Hello and welcome to my lecture for Philosophy 4400 on the reversibility objection. So this lecture is going to be about a problem that David Albert discusses for the explanation of the entropy law that we discussed in the previous lecture. Now, I assume that you listened to the previous lecture about entropy. If you haven't, go back and listen to that. But just as a brief review, we said that the entropy law, the law that entropy is constantly increasing, can be explained by these assumptions. First, atomic theory, that all of the material objects around us are made of a very large number of tiny particles in random motion. Second, classical mechanics applied to these particles. And third, ordinary probabilistic reasoning starting from an application of the principle of indifference, namely where you assign a uniform probability distribution over regions of the phase space for your physical system. Now, the problem with this is all of those assumptions that I just mentioned are temporally symmetric. That is, none of those assumptions contain any kind of asymmetry between the past and the future. None of them say anything that would imply that the past direction of time is importantly different from the future direction. But the entropy law is temporally asymmetric. It specifically says that entropy increases in the future direction and not in the past. And as usually understood, we expect that entropy goes down in the past direction just as it goes up in the future direction. So how can we get this temporal asymmetry when the explanation for the entropy law relies on physical assumptions that don't have any temporal asymmetry? Now, this is an example of what I mean about being temporally symmetric. So you have laws of physics like F equals ma, the famous Newton's second law. There's no temporal asymmetry in this. So if you have, you can have a negative F being equal to m times negative a, and that would be an equally good solution. In other words, if you have a certain sequence going forward in time, you can take a time reverse of that sequence and it will still satisfy the laws. So that's what I mean by there not being an asymmetry, a temporal asymmetry in the laws. Okay, now to make this problem sharper, we can consider a couple of arguments that somebody could give in favor of what I call the reverse entropy law or the two-way entropy law. So the reverse entropy law would be the law that entropy increases in the past direction in time. The normal entropy law says that entropy increases in the future direction in time. Okay, or we might have the two-way entropy law, which says that entropy increases in both directions. So in other words, the two-way entropy law says if you're in a state that's highly ordered, you should expect that both in the future of that state and in the past of that state, the universe moves towards thermal equilibrium. So the highly ordered state probably arose from thermal equilibrium and is shortly returning to thermal equilibrium. Okay, so here's the argument for why you should believe reverse entropy or two-way entropy. So assume that a physical system is in a certain macro state, M, which is not in thermal equilibrium. So it's an ordered state. The overwhelming majority of microstates that are compatible with M evolve forward to thermal equilibrium. And that's just what we were saying in the previous lecture to explain why the second law of thermodynamics is true to begin with. And so, but there's the problem that for every microstate that evolves forward to thermal equilibrium, there exists exactly one corresponding microstate that evolves backward to thermal equilibrium. Or in other words, exactly one microstate such that it would have arisen from thermal equilibrium in the past. How do I know that? Well, you just take the time reverse of the earlier microstate. So if there's a microstate that will evolve forward to thermal equilibrium in the future, then if you just take the same state but reverse the direction of all of the velocities, then you get a microstate that, quote, evolves backward to thermal equilibrium, or more colloquially, a microstate that would have arisen from thermal equilibrium in the past. Right, and so therefore, it looks like the measure of the states that arose from thermal equilibrium has to be equal to the measure of the states that evolve toward thermal equilibrium. So the probability that the system evolved from thermal equilibrium in the past should be equal to the probability that it will go to thermal equilibrium in the future. Here's a second argument for the same conclusion, the two-way entropy law. Almost all of the phase space is occupied by thermal equilibrium states. And that's just, again, the point that we made in the previous lecture in trying to explain why you should expect entropy to increase in the future. And also in the previous lecture, we assumed that your physical system evolves on an ergodic trajectory. And so, as we said before, it will probably soon move to thermal equilibrium and remain there for a long time simply because almost all of the phase space is thermal equilibrium. But exactly the same reasoning suggests that it probably recently came from thermal equilibrium and was there for a long time. So in other words, because almost all of the phase space is thermal equilibrium, that means that the most likely state for the system to be headed towards is thermal equilibrium. It also means that the most likely state for the system to have just come from is thermal equilibrium. Also, over a long period of time, if you think about it, the number of transitions from low to high entropy states should be equal to the number of transitions from high to low entropy states. Now, to explain a little bit more why that's true, I introduced this principle known as the Poincaré recurrence theorem. So the diagram here is supposed to represent schematically a system moving around its phase space. Obviously, of course, the phase space would be more than two-dimensional, and more than three-dimensional, as this picture is. Okay, but just for the conceptual point, a system will move around the phase space in this kind of pattern where it has a long cycle and eventually comes back to where it started or approximately where it started. So the point in this diagram represents the whole physical system. And all of these lines represent possible trajectories that it can take through phase space. So the Poincaré recurrence theorem says if you have a physical system that's confined to a bounded region of phase space, then it's going to repeat its initial conditions to any desired degree of approximation infinitely many times. Okay, now this condition that you're confined to a bounded region of phase space is non-trivial, but that would be true if you're limited to a limited region of physical space and you have a fixed total energy, right? Then you have to have a bounded region of phase space. On the other hand, if the universe is expanding infinitely forever, then the phase space is unbounded. Okay, so we don't know for sure that these conditions obtain for this theorem, but it is nevertheless an interesting result, and it may well be true. Okay, I note also that the eternal recurrence is the way that Nietzsche thought about the eternal recurrence. It was an exact repetition. So he thought that everything that's occurring now will repeat exactly in every detail at some time in the future. The Poincaré recurrence theorem doesn't support this, but it does support that you can get an approximate recurrence. So in other words, there will be a future state that is as close as you like to the current state, but with at least some non-zero degree of approximation. Why does the Poincaré recurrence theorem hold? So the basic idea is as the system moves around the phase space, if you're in a bounded region of phase space, it's just going to eventually run out of new places to go, so to speak. So it's going to have to at least come close to its initial position. Also, if we assume determinism, so we're leaving aside quantum mechanics, if you assume determinism, the paths through phase space cannot cross. So after it gets back to its initial position, it's going to just repeat the entire cycle. If it comes close to the initial position, then it will do something that's kind of close to repeating the original cycle. What does this have to do with the two-way entropy law? Well, it shows that there have to be equal numbers of transitions from high to low entropy as there are from low to high entropy. So if you think about the low entropy regions of the phase space, if you're on a giant cycle that's constantly repeating infinitely many times over the long term, over the infinitely many times that this cycle occurs, half the time you're going from a low to a high entropy region, half the time you're going from high to low entropy. To think of it in terms of a simple analogy, if you have something moving around a circle over and over again, and it moves into a particular arc of the circle, every time it moves into that arc, it subsequently moves out. There is exactly the same number of transitions into the arc as out of the particular arc. Okay, and so all of this is leading to, apparently, the two-way entropy law, which would say that if you have a physical system that is not in thermal equilibrium at time t, then its entropy probably increases both in the past and in the future direction relative to t. So if it's a highly ordered state at t, then after t it will probably be more disordered. Also before t it was probably more disordered in an exactly symmetric way. Now I note that this is not an accepted law, obviously, even though I called it the two-way entropy law. This is not a correct law, but the philosophical question is, why not? Why do we not accept this law? The problem is that this is completely insane. So if you think about what this means, first think about our ordinary understanding of entropy and think of some examples of illustrations of entropy. So one of the illustrations is if you see a young person, you expect that person to grow older in the future and eventually die, and then their body will eventually decay and turn into dust. If the two-way entropy law is correct, then you should expect a mirror image of that process to exist in the history of that person. So exactly as you think they're going to get older in the future, if two-way entropy holds, you should think that they were older in the past. In fact, you should think that they originated with a pile of dust which spontaneously assembled itself into a corpse, and then sometime after that the corpse came to life as an old person, and then it aged in reverse to reach the state of the young person that you see today, right? Exactly a time reverse of what you think is going to happen in the future, right? Or to take another example, suppose you see an object in the air, and you don't get to see how it got there, but you just get a quick glimpse of a heavy object that's sitting in the air. And what you expect to happen is you expect it to fall to the ground, and then it's going to hit the ground and the energy will dissipate into the ground. So the kinetic energy of the rock will get converted into sound waves and heat in the ground. Okay, if the two-way entropy law is correct, you should expect that the history of that rock is also a mirror image of that. So the history of it is probably it was sitting on the ground for a while, and then molecules far away started kind of moving towards where the rock is, right? And so this is like the time reverse of the energy being dissipated as heat, right? And just coincidentally, a whole bunch of molecules in the ground happened to be on trajectories that would lead them to hit the bottom of the rock at a particular time and knock it up into the air. And that's probably how it got into the air. Needless to say, these are insane expectations. Nobody thinks that these things are the case, but the question is, why is it that we think that a completely different thing is going to happen in the future than the thing that we think happened in the past? Where do we get the temporal asymmetry given the temporal symmetry in the fundamental laws of physics? Okay, now we're going to talk about David Albert's solution to this problem. So as Albert notes, and as we've just seen, if you give a uniform initial probability distribution over the phase space, that is not consistent with our actual beliefs about the past. right? So in other words, by uniform probability distribution, I mean you think that equal-sized regions of the phase space are equally likely to be the actual state of the universe, right? And so you would say, you would observe the current macro state of the universe, and then say every micro state that is compatible with what we observe is equally likely. Okay, if you do that, then you get the two-way entropy law and you get all these insane predictions. And so it's just not consistent with what we think is actually the case about the past. And so Albert's solution is to just introduce this principle called the past hypothesis. This is the hypothesis that, the universe just started out in an incredibly low entropy state. And there's no explanation for why it was that. It just was that way for no particular reason. And we're just stipulating that our theory says that's how the universe started out. Okay, and then instead of assuming that you should give a uniform probability distribution over the region of phase space that's consistent with the current state of the universe, we assume that you should give a uniform probability distribution over the phase space consistent with the past hypothesis and the current observed state of the universe. So if you do that, then that gives you the correct predictions and explanations. That gives you the standard one-way entropy, where entropy increases in the future and not in the past, and so on. Now, here's the problem, but how would the past hypothesis be justified? So plausibly, you could argue at least, our evidence consists entirely of facts about the present macro state of the world. That is, you might think what we're actually observing and that we're directly aware of is only the current state of the universe. So right now, we're observing the current state of the universe. Maybe in the past, we observed the past state of the universe, but we don't now have that directly available to us. We only have the current state directly available to us at the current time. Okay, but if you're just given the current macro state and the laws, not including the past hypothesis, and you're asked to assess how likely the past hypothesis itself is, the answer is that it's incredibly improbable. And so the question is how you would know that the past hypothesis is true. How is that justified? Right? What Albert says about this is, well, the past hypothesis is justified in the same way that our beliefs about the laws of nature are justified. Namely, the past hypothesis is successful at predicting lots of observations that we have, including the observations that we have had in the past that we remember. So that's what David Albert says. But the problem with this is that this answer just requires assuming that our beliefs about the past are correct and that we know this. But the problem is that if we're entertaining the two-way entropy law, we can't assume that. So our memories about the past, our memories are only reliable indicators of the past if the one-way entropy law is correct. So in our ordinary understanding, we think that what's going to happen is, our bodies are going to progressively deteriorate over time, and what will happen in the future is completely different from what our memories represent about happening in the past. But if the two-way entropy law is correct, then we should think the same thing about the past that we think about the future. We should think that our memories, the way that our memories probably arose, is similar to what we think is likely to happen to us in the future. Right? So we should think that our memories arose by a bunch of material kind of just happening to come together and arrange itself into the current configuration of our brain. We should not think that events actually happened in the past that are like the things that we remember. That is, we should think that the probability of that is exactly the same as the probability that in the future a bunch of stuff is going to happen that's just like what we seem to remember, right? And so I don't think that we can just assume that our beliefs about the past are correct and that we know this in order to explain how we know that the two-way entropy law is not correct. It doesn't help to postulate that the past hypothesis is, quote, a law of nature, as has been suggested by at least some articles in the philosophy of science literature. Because if you can postulate the past hypothesis as a law of nature, then any other possible starting condition of the universe could also be postulated as a possible law of nature. And there are many more starting conditions leading to the current state from thermal equilibrium than there are that would lead to the current state from a low entropy Big Bang. And that, by the way, is uncontroversial, and that is just supported by all the preceding reasoning that we've been doing about the two-way entropy law. And so you still have to explain why it wouldn't be more probable that the correct law of nature has it that the universe started at thermal equilibrium and then moved to the current state, rather than the law being the past hypothesis. The British mathematician Roger Penrose has calculated that the probability of the postulated initial state of the universe, the state that we think that it was actually in at the time of the Big Bang, is something in the neighborhood of 1 in 10 to the 10 to the 124 power. So it seems like some kind of explanation is required for why the universe happened to be in that state. I think I know what David Albert would say about this. I think he would say, well, we can't assume that a uniform initial probability density over the phase space is the correct starting point. But the problem is that he hasn't given any other proposed probability distribution that would be the correct starting point or explained why some other distribution would be correct. So we still don't really have an explanation for what we needed explained, right? Namely, why we're not justified in believing in the two-way entropy law and things like that. Okay, here's a related objection. I call this the 1950 objection. So imagine putting forward the hypothesis that the universe started in the year 1950. So we take the universe to have been in a certain physical state at that time. Suppose somebody says, yeah, maybe that was the first moment of time. And it just started out in that state, exactly the state that we think it was in 1950, except there just wasn't anything at all before that. Now, you might think that this is an insane theory, but actually it looks like this theory is better than the standard Big Bang theory. It predicts all of our observations equally well, assuming that you were born after 1950. All of your observations have occurred since then, so all of your observations are equally well explained. And you might find it troubling that it just has this inexplicable initial state. There's no explanation of why the universe was in that state in 1950, but that's no worse than the standard Big Bang theory. We just have this initial state and there's no explanation for that either, right? And that's basically David Albert's view. So why can't I put forward this analogous theory where we just started in the 1950 state? And also, by the way, the 1950 theory has a higher initial probability because the state the universe was in 1950, that has a higher prior probability than the state it was in allegedly at the time of the Big Bang, and actually higher by many orders of magnitude. And how do I know that? Basically, this just follows from the fact that the universe has been increasing in entropy since the time of the Big Bang, at least according to standard views. So the entropy of the universe in the year 1950 is uncontroversially much greater than what we take it to have been in at the time of the Big Bang, which means the 1950 state has a higher prior probability if you're assigning equal probabilities to equal-sized regions of the phase space. Now you might have this objection. You might think, well, maybe there's no way of assigning probabilities to the initial state of the universe. Now, I don't know why. Maybe you have a problem with a priori probabilities in general, so maybe you think there's no way of assigning any a priori probability, or maybe just have a problem with prior probabilities for initial states because maybe you think that probabilities always have to be conditional on some information about the actual state of the universe. Whatever. Let's say you think that we don't know what the prior probability should be, and there's no correct probability distribution for the initial state of the universe. But still, in that case, you still don't have any reason why the 1950 theory would be worse than the Big Bang theory, because the same thing would be true about the Big Bang theory. Then you would have no way of assigning the initial probability to the Big Bang state, just as you have no way of assigning the initial probability to the 1950 state. So there's just no way of saying if one of them is more initially probable than the other. Meanwhile, on all other criteria of the theory are equally good. So what we have is at least the 1950 theory is no worse than the Big Bang theory. So in conclusion, entropy remains a mystery. We still don't know why our universe started out in such an incredibly low entropy state. And also, as an epistemological problem, it's not easy to explain why we're justified in believing that it did.